Ladies and gentlemen, our next session begins now, so please help me welcome Jennifer Marsman.
Hello, everyone. I hope you enjoyed the break. So what I want to talk to you about today is kind of a meandering story, but hopefully it will all come together at the end. This work all started when myself and a colleague of mine, I do machine learning work at Microsoft, and myself and a colleague of mine by the name of Weiyang Tak got together, and we were asked to create a big demo that we could show like on stage at a big Microsoft conference, something like that. And we both do machine learning work. He's a data scientist in the Azure machine learning team. And so the two of us got together and we're like, okay, we have to come up with some cool demo that shows some cool machine learning stuff that Microsoft has done. And we're putting our heads together, and Weiyang got fixated really early on the idea of doing something with drones. I think he just really wanted an excuse to expense a drone, right? So he's like, drones, we gotta do something with drones. And when this work started, this was like about a year plus some ago. And this was, how many of you guys watch Game of Thrones? All right. So this was when the hardcore stuff was going down on the show, right? The Hodor episode had just happened. Like, Daenerys had just burned down all the cause. Like, it was wild. People were taking time off work to recover, right? All right, so all this stuff was happening. And so this was totally in my head. And also, much like Weiyang, I was thinking, okay, we want to do drones. We want to do machine learning. We have these amazing, facial recognition APIs and such. And so, much like Weiyang, I'm like, okay, here's a great way to be able to expense a really expensive Daenerys Targaryen costume. What if we had the drones be my dragons, and I walk on stage, and I can get my 3 dragons to follow me? So we're just going nuts with all of these silly ideas for what we could do. But then at some point, reality set in, and the first major decision we had to make was to decide, what kind of drone are we going to buy? And so that's when it's really nice to work at a big company like Microsoft or Google or Amazon would probably be very similar. It's a huge company. There's a lot of people doing work in a lot of different areas. So we started nosing around, asking, is there anyone else doing work with drones and work with machine learning, and what else is going on? And that's when the third person on that slide, Ranveer Chandra, came in to our stuff. So Ranveer works for Microsoft Research, and he is doing some amazing work around using machine learning together with IoT, drones, and some neat networking research to be able to essentially try to solve world hunger. So let me tell you a little bit about that first, and then we'll get back to the Game of Thrones stuff in just a second. All right, so the issue that they're trying to tackle is the idea of we need to increase our rate of food production. So there's some data that was released at the United Nations in 2009. And at this big UN summit, someone made a big presentation that by the year 2050, the world is going to have 9 billion people. And we essentially need to double our current rate of food production to be able to feed all of these people. And so what Ranveer was really looking at is, okay, how can we use technology to improve the yield, the overall yield of food production? So enter the concept of precision agriculture. So I was not familiar with this concept prior to coming into this project, but the idea is that right now, when you're a farmer and you water your fields, typically fields are watered homogeneously, right? You have a big sprinkler and you water every part of the field the exact same amount. However, the idea of precision agriculture is that fields aren't actually uniform. If there's a little, dip in the field or something, then the water's going to run down, and that area is actually watered a little better than, the slope or the top of the runoff. So you can use that information to be able to only water exactly, the parts of the field that you need, and that saves water, and then you can use that information in conjunction with other things to work on increasing yield. And then there's a whole lot of work that's being done in other areas as well around collecting other information to give a better distributed look at the farm. But what I heard from, and so there's an obvious solution to that, right? Any of you guys who are engineers or developers or tinkerers may have played with some IoT stuff, and may have seen that it's pretty cheap to get these little moisture sensors in the ground. So okay, that makes sense. You put some moisture sensors in the ground, and then we can use precision irrigation, for example, to only water what needs to be watered. However, what Vanvio told me is that it costs approximately $1,000 per sensor to implement this. And I was like, you sure about that? Can you check your numbers? Because I can just pull up adafruit.com right now, and here's these moisture sensors. They're actually pretty cheap. And it turns out the actual cost of the sensor is negligible. That's not that expensive. So where is this extra money coming from? And it turns out that the next thought I had is, okay, power, right? You need to provide power to these sensors, so maybe that's where the issue is. However, they actually derive power through solar panels. So there's a nice solar panel that can collect the rays of the sun and convert that into energy, and it's not that much, but the little IoT boards don't need that much power to run, so you can actually do it primarily just through a solar panel. And solar panels are maybe $100. I mean, it's not that expensive. It's not $1,000 per sensor. So where is that extra cost coming from? If we have the sensor, the power taken care of, it turns out what is actually contributing to that $1,000 a sensor cost is connectivity. That's the hard part. When you think about, if any of you have ever driven through a more rural area and tried to get cell phone coverage or that sort of thing, you know that the cellular towers are less motivated to provide great coverage in more rural areas. And then if we want to do some of these things in third world countries as well, they don't always have the cellular infrastructure that's there. And then there's other technologies like wireless, but when you're considering like a 1,000-acre farm that some of these farmers have, you would need so many wireless access points to make that happen. So that's another one of the challenges that they were tackling, and I'll talk a little bit more about that later. All right, so where does the machine learning come in, and where do the drones come in? Let's talk about that. So if we can assume for right now that we want to limit the number of sensors that we have available just because of this cost. So what we can do is put a smaller number of sensors throughout the fields, but then use that sensor data in conjunction with aerial imagery from drones, okay? So if we fly over fields and take aerial imagery of drones, then we're going to get information like how green versus how brown things are and kind of what those things look like. And then taking that aerial imagery from drones flying over the farm in conjunction with that sensor data that we're getting from those moisture IoT sensors, we can apply machine learning models to that and extrapolate the value so that we get moisture levels for the entire field, even the ones that don't have sensor coverage. Okay? So that's what we're going to try to dig into a little bit more deeply. So we have these cameras, these drones, these sensors all feeding data, and this is part of a larger project called FarmBeats, where they're trying to give the farmers an all-up look at their farm. So they also feed in things like weather data and things like that, and then can produce various insights, also using machine learning, things like the ideal time to plant, where are the best areas to plant which crops, all kinds of other cool things like that that can improve yield overall. All right, so here's a quick look at the farms, just because these are kind of fun to look at. So Microsoft actually is implementing some of these techniques that we're talking about in a 2,000-acre farm in upstate New York. So again, when you think about connectivity over 2,000 acres, like that's kind of a challenging problem. And then we also have a smaller farm, about 100 acres, so still big, but a 100-acre farm in Carnation, Washington, which is very close to where Microsoft's main headquarters is in the Redmond area, which is a suburb of Seattle. And so if you take a look at what you can do with these drones now, we have the drones kind of flying overhead, and I can show you a quick little animation of this. And so this is the drone flying over this farmland, and then these are the pictures that the drone is taking at each of the red dots, at each of the positions there. So right here you can see it's about to make a turn, and you'll be able to see that, woo, see how the landscape is turning as it makes this little turn right here. Cool. So obviously if we're taking pictures every so often, then on the back end you can stitch that all together and get a nice all-up view of what the farm actually looks like. All right, then the next thing to think about is sensor placement. So we can actually use machine learning as well to determine where can we best place those sensors to be able to extrapolate the data the best. And so there's a lot of neat things you can do with kind of the aerial imagery like this. One of the things is weed detection. So thinking about just when you have aerial imagery like that, can you see like where weeds are popping up? You know, if you're dealing with a 2,000-acre farm, just managing all of that can be overwhelming. So knowing where are the weeds coming up and what areas are best to let the cattle graze, right? Like in this area, it's still very green and there's a lot of grass available. In this area, they've eaten most of it, like that sort of thing. So just knowing too where to put your herds is another really cool thing you can do with this aerial imagery. But we can use this to place the sensors in the most optimal positions to be able to extrapolate data. So maybe one right here, kind of in that green area, maybe one over there, and one near the edge where that little water line is, and then be able to use that to extrapolate across the whole field. All right, and here's what the sensors actually look like on the ground. So we have a little board here, and we have it enclosed in a waterproof casing, since these things are living outside. So it's in a waterproof case, but the little sensors, the measuring, the things that can measure moisture are, stick out of the waterproof case, and those actually get embedded in the dirt. And then we measure at 2 different levels. I think it's like 4 inches under and 12 inches under, so you get 2 different moisture levels on how deep and how much moisture there is. And then you can see the little solar panel at the top, and then that reads and provides power and charges it as well. And then there's actually a little infrared camera on here as well, so you can get imagery of kind of the surrounding area and just see what it looks like. It's really cool too for measuring things like the spread of pests and other things, but you can see, all right, in this area, these things look like they're dying a little bit, and even with the infrared camera, you can see that at night as well. All right, so here's where some of the machine learning comes in. So we're actually using Gaussian processes to do this, because you can assume a nice, normal distribution. And there's really 2 kind of things we're trying to balance here. So one thing is the spatial smoothness factor. So since we're measuring like the soil and kind of what that environment looks like, if there's things that are nearby, so here's this green area, another green area right next to it, like those things are probably going to have similar readings. They've probably been watered the same amount similarly. So you can assume some stuff through proximity, right? And then secondly, areas that look similar should have similar sensor values. So if we have 2 patches of area that are both kind of the same shade of darkness, that have both been watered recently, if they're kind of the same shade of darkness, there's some assumptions that you can make around, okay, they probably have a similar amount of moisture, like that sort of thing. So there's neat things we can do to tie those together as well. All right, and then to put that all together, we have now our sensor data that are coming from those things that you saw, the IoT, the little board, that's getting sent to the cloud, and then you can use that together with the data from the drone. And I'll talk a little bit more about the drone data in a second, but we actually send a drone up, fly it over that farmland, and then we don't stream it in real time. We just collect all the data like on the drone, so it's storage on like a USB drive, portable storage that's on the drone, and then we bring it back down and then stitch together the imagery after that. But what it can give you then is this great spatiotemporal view of the farm. So we can measure things like, here are the irrigation levels across the farm. Here are the pH levels, the fertilization levels, the temperature, across different areas of the farm. So it's very, very cool things. And then this can lead to a whole bunch of agricultural services. So the yield estimation I mentioned is a huge problem, a really cool thing that we're trying to increase. I talked about precision irrigation, and that can be applied not only to how much you water, but fertilization, pH levels, all of those things. Only put fertilizer on where it's needed versus homogeneously doing it is the precision fertilization, et cetera. So we can apply that to several farming techniques. And then the spread of pests as well is kind of an interesting problem, like being able to predict where they are and where they're going and that sort of thing. So there's all kinds of neat agricultural services that can come out of machine learning processes here. All right, so a little bit more about the drones and kind of how we're doing this from the drone side. I want to talk about kind of the issues that they had along 3 axes. The first one is the drone capabilities, so what the drones can do. And so if you're a farmer, we don't want you to have to be an expert in drone manipulation and flying drones to be able to do this. Like, we wanted to make it like easy for anyone to be able to do. And so they wrote an iOS app that will allow the farmers to do this. And there's 2 different modes it can work in. You can do a point selection mode where you just kind of specify, okay, I want you to follow this path, and it'll just follow a path along those points. Or you can do area selection mode where, again, you select a bunch of areas or a bunch of paths, but that's kind of the boundary that you want, and then it will fly back and forth between there and cover that entire area. And then it does all kinds of things. It can store flight paths. It gives you a checklist. I can show you a little video of it right here. So this is one example of the the drone, a farmer. It's a little video of a farmer using this. So first of all, he maps an area on there, and so it's dynamically choosing a route for it. He sets the altitude, so you can choose how high you want the drone to fly over the crops based on what you're doing. You can save off and store that path, so that flight history, so in case you want to fly that drone over the same area again, you can do that. So that's our carnation farm. And then there's a nice checklist so you can remember, oh yeah, did I remove the thing from the gimbal so that the camera can freely move, and did I charge the battery, and all of those types of things. And then it should, hopefully, you hear it? Yeah, that's the drone taking off. You can kind of hear it in the background. So pretty cool stuff. Okay, the next issue with drones is power consumption and battery life. Any of you guys have a drone at home? Okay, cool, a bunch of people. All right, so with drones, you know that even the best drones maybe have like 40 minutes flight time, right? Like the batteries don't last that long. They need to be swapped out fairly frequently. I brought a spare with me, and hopefully this guy is good for the life of the talk. But battery life is a huge issue with drones because they're flying, they're fighting the wind, they're doing all kinds of things to stay in place, and so battery usage can be a huge issue. So there's two main things that we did to combat that. So when we are using an algorithm to develop the path that the drone should fly, we did two main things. The first thing is that the drone actually uses more battery and more power when it is trying to stop and slow itself down and like change directions. Like those things are the most heavy usage of power. And so the way you can obviously figure that out with a little bit of math background is that it makes more sense to have it fly the long direction rather than the short direction, right? So if you have it fly, if you want to reduce the number of times it's stopping and slowing and changing direction, then if you fly the long path, then obviously you only need to change direction 8 times, for example. And if I'm flying the width of it instead of the length, essentially, then I have to change direction 16 times. So they always choose the long path over a given area to optimize the battery usage there. And then the second thing is a yaw algorithm. But to explain that, I first have to explain one little background detail about drones, and that is that there's 2 types of drones. There's this omnidirectional one, which is essentially symmetrical, right? It looks the same from the front or the side. And then there's also directional ones, and this bad boy I have here is a directional one, where you can see it actually looks a little bit different from the side. It kind of, you can have them, you can see it kind of goes down, so there's different amounts of drag, and wind resistance changes whether you're looking at it like this or like this. It's going to give different resistance to the wind. So what they've also developed is a yaw control algorithm. So what that means is that if we have information about the wind and we have the drone's path that it's flying, what we can do is actually change the yaw of the drone to conserve or save energy. So imagine, if the wind was blowing this way and I wanted to accelerate, I can kind of tip like this, tip the drone like this, and then it'll utilize the wind and fly faster. And then when I want to slow down, I kind of go like this, and then that will utilize the drag and increase the drag, the wind resistance, and then it's using less battery and it's using more of the wind. So kind of acting that out in interpretive dance there. But that makes sense, right? Cool? Okay. Awesome. All right, and then the final piece is the networking challenge. So I talked about this at the beginning, that $1,000 per sensor issue that we were having, and how could we fix that? And so if you look at what kind of wireless technologies are available today, we have all kinds of options, everything from like RFID, which you have to be very, very close for it to work, and it's fairly low throughput, to Wi-Fi, where it's kind of got a bigger range, but it really only lasts the range of your house pretty much. If you go out to your across the street, you're going to lose your wireless signal. So all kinds of different things, and then cellular and that sort of thing. But there was nothing that was really good for stretching over these 2,000-acre farms. And so that's where some cool networking research that Ranveer was working on came in. And he was one of the people who was pioneering the idea of television white spaces. So essentially what this means, a little bit of background, if you're dealing with conventional Wi-Fi, that operates typically in about the 5 gigahertz range frequency. And if you're dealing with TV, television signals, as a television station broadcasts out its channel data, that stretches, it's a lower frequency, so it stretches a lot further, right? So you can broadcast much, much, much further to make that work. So the idea is to utilize unused television channels to send data packets and create your own little internet there. All right? So pretty cool, pretty cool stuff. I mean, obviously you have to work with the local government. You can't just go sending stuff over unused television channels willy-nilly. But it's really cool if you look at some of the areas where we've done this in rural areas and in third world countries. There's some really neat opportunities here. And even that, like we're talking about doing this in some of the urban areas in a big city to be able to have, wireless available connectivity available for everyone. Like it's a really, really cool thing. And the idea of just being able to connect to my home internet essentially from 10 miles away is just so exciting to me. Who would not want that? So yay. So we've actually done this and prototyped it in Kenya. So here's one example where we did some work in Kenya, standing this up for a village there. And it was very, and that prototype was pretty successful. And then Ranveer actually went to Ranveer actually went to India about a couple of months ago and was standing up a thing there as well. So pretty cool work there. Okay, so I don't actually have one of the farm drones with me because they're busy doing farming work and we don't have fields here, so their data would not be useful anyway. But what I'm going to try to do, and I'm actually going to do a cheaty way of this, is a really bad demo. And the reason it's going to be really bad is because there is a lot of moving pieces that need to make this work because I'm relying on cellular data. I'm running this over a MiFi, which is kind of crazy. I need GPS to orient the drone, and we're in this beautiful structure with lots of stuff that likes to block signal and all kinds of things. So I did a quick test, and then we also have a little draft going this way. So I did test this beforehand, and it looks like the drone was being unresponsive, and basically it wasn't listening to my controller. So just for safety reasons, because I want Courtney to invite me back, I'm not going to actually fly the drone. But what I'm going to do is a cheesy half thing, because I still really want to show you my demo because I worked really hard on building my facial identification model, so I want you to see it. Okay, so what I'm going to do instead is first I'm going to do this. I'm going to, here's the hacky way we're going to do this. All right, so what I have here is a drone. I'm flying the DJI Maverick Pro right now. And I have an iOS app on here that we wrote. And I'm going to try to connect through AirPlay. Come on. Oh, wow. If all of this works, I will be so impressed, you guys. All right, so so you can see what's coming through on this phone. And then what we're going to do is I'm going to do a cheesy version of this where I'm not actually going to fly the drone just because of safety reasons, because it was being unresponsive. I don't want to get sued later if it goes like that and heads into the audience and the blades get somebody. So what we're going to do instead is a cheesy version of this, I think, just so I do actually show something. I'm going to do, nice dragon drone icon, right? Okay. Now, are you still awake, baby? Here. Let me just make sure everybody is online right now. You should be on the same internet. Yes. As you. Yes. Okay. Then let's try that one more time. And again, I will not be. There's a lot of, why talk about cool research when you could do a demo that relies on 25 billion moving parts to make it actually work, right? Okay, so we're going to try this once and see if it works. Come on, baby, you can do this. Why are you not coming through? All right, let me try this one more time. We're going to do this. We're going to kill this. No, just come on. Whew. All right. Now I'm going to do this and take it out real quick. And then reattach it. And then if it doesn't work, we'll we go. And now relaunch. Nice, okay. So what I'm going to do instead is a really cheesy thing where instead of actually flying the drone and having it recognize me or whatever, I am going to just hold the drone and point it at me. I know, right? So lame, so lame, so lame. So it does actually work, trust me, when we don't have so much cell signal. So hopefully the lighting is okay, right there. Can we turn the house lights on? Or it's fine, let's just do it. All right, so 1, 2, and it's not usually trained on something that's so close to me, so let's see how that works. All right, so what's happening now is it is calling the Microsoft Cognitive Services, and yay, it worked, yay! So Drogon would have recognized his Khaleesi, all right? And then I'm going to make him like do flips or something too. Okay, so that is the short version of it. All right, so now let me just close with, I'll show this video. What are we doing after
This area is known as Stewart's Landing, and this is Dancing Crow Farm.
One of the world's problems is yield. How do you double the yield by 2050 to feed the growth of the population in the world? That we recently started, what we want to do is we want to enable data-driven farming. The first goal is to give a real-time view of the farm, the real-time pulse of the farm to the farmer, saying, hey, this is what your farm is doing right now. So how do you even connect these farms to the internet? It's so far remote, the cell carriers have very little incentive to provide connectivity in the farms.
The system that we have deployed here is measuring soil temperature and moisture, and it's coming from this sensor.
Here what you see is a white spaces device. The idea that we had was a farmer buys a white space router, plug it in the farm, and your entire farm is connected. Now you can connect multiple devices, and connectivity is cheap. So you can actually deploy many more sensors in the farm. You could have a dense deployment of sensors getting real-time view of all the parts of the farm. Not only your soil and moisture data, but this is a high bandwidth connection. You can connect cameras, get real-time views from the farm. So once you have all this data, you could then analyze the data to predict what the future would look like.
I'm actually really looking forward to how the process will change. This last year has been mainly a data gathering, information collecting year for the Microsoft research team. I'm really looking forward to seeing what research they've gathered this year, putting that together with what I think is going to happen next year, and make predictions for what I should plant when and where.
So this is how we could maybe take a step closer to solving world hunger using drones, cutting-edge networking research, IoT, and machine learning. I'm going to skip through. There's a bunch of great resources. I put them into a bit.ly-like thing, a shortened thing. If you want to just go to ak.ms/gen-farm, there's a whole bunch more resources on this project available. And then I have all kinds of answers about like results and such, which I'm happy to share later. Thank you guys so much.
Thank you, Jennifer. Ladies and gentlemen, please help me welcome our next speaker, Jeremy Nixon.
Hello? Perfect. Makes sense. So wonderful. Thank you very much for the applause. I am a researcher and an implementer of these sort of distributed deep learning libraries inside of Spark. And so this talk is going to be about new algorithms that we've developed in Spark, so specifically about convolutional neural networks and doing it at big data scale inside of MLlib. So just a little bit about me. I'm basically an engineer at the Spark Technology Center, and I contribute to MLlib. So MLlib is Spark's deep learning library, and I've been working on scalable deep learning inside of it. Before I was at the Spark Technology Center, I studied applied math to CS and econ at Harvard. So this audience is basically very machine learning focused, and so I guess I want to talk a little bit about Apache Spark, why it's valuable, why so many people are using it for ETL, and why it'll be useful to integrate machine learning with the rest of your analytics loads. So about Spark, so basically it's for doing large-scale data processing. In general, when people are doing large-scale data processing, they'll have their data in HDFS, so in Hadoop, and Hadoop has this default computation paradigm of MapReduce. So Spark created this innovation where instead of basically doing iterations by writing to disk and reading from disk over and over and over again. So in the case of machine learning algorithms like logistic regression and like neural networks, where you're basically computing a gradient over and over again, you'd have these extraordinarily slow workloads. Spark basically allows you to do these computations in memory across a large compute cluster. And so for these iterated jobs, you have like 10 to 100 times speedups for things that are reading and writing to disk in HDFS. There's also this improved usability. So the API that most data scientists want to use in Python and PySpark has been made available, and that was actually a real difficulty in doing data science on top of extraordinarily large data sets. There are also Java and Scala APIs, so sort of like classic analytics workloads, and people who are comfortable with those tools are basically using them. And basically MLlib is implemented in Scala, so a lot of the code that we're writing is this like distributed Scala database. So this is a little bit about MLlib. So MLlib is Spark's machine learning library. It's basically a packet of tools, very basic tools for doing large-scale data analytics. And so we have alternating least squares. So if you're trying to create a recommendation engine, you can use that for collaborative filtering. If you're basically trying to do linear logistic regression, you have those options. There are decision trees, naive Bayes, and SVMs. But when I joined the SDC, one of the major things that was missing was basically being able to do large-scale deep learning with MLlib. And so this is about adding one major algorithm that's gotten state-of-the-art results on lots and lots of important tasks. Advantages to MLlib include it being integrated into Spark. So basically, when you're doing ETL, Spark is extraordinarily efficient. You also often want to do machine learning on top of that. And so you'll have a single integrated environment in which to do all of your data analytics. It's like extremely scalable and has like a nice body of APIs as well. As far as deep learning and MLlib is concerned, advantages include basically the benefit from extremely large data sets. So for example, if you have a huge number of images, so I guess like Flickr had this data set with hundreds of millions of images, storing that in HDFS and doing the compute with Spark allows you to do extraordinarily large data analysis. And for deep learning, this makes a lot of sense because you have these extremely large models, and in order to get sufficiently low variance, you're going to want to add as much data as possible. And the accuracy will scale with the data much more efficiently than with other algorithms. Spark makes this large-scale data analysis really easy because it has this RDD, resilient distributed data set, which will distribute your data across the cluster efficiently. And by doing it in MLlib, the compute will be local to the data. So basically, you won't have to move your data, this extraordinarily large data set, from this distributed Hadoop cluster to an entirely different node or set of nodes in order to do deep learning on them. Everything's integrated into Sparx Pipelines, which is also extremely convenient. So here's a few links to this package for doing deep learning. You'll see this again later in the talk. But basically, the structure of this talk will look at first framing deep learning. So I guess from the perspective of a researcher and from a data scientist, how do you think about improving these models, and how do you think about in what contexts you should apply, in this case, convolutional neural networks, but in general, different machine learning algorithms. Second, I'll walk you through this MLlib-based deep learning API. You'll actually be pretty familiar with it. So I guess, does anyone here use Keras? Yeah. So I guess this API is the Scala analog of Keras, and so you'll be able to do import-export from that library. So I guess anything that allows you to do import-export into Keras. But you'll also be really familiar with the API to begin with. So you'll see that in a little bit. And after that, I guess I want to talk about optimization. So basically, we've implemented a lot of modern optimizers, which lead to dramatic improvements in both the performance of the algorithm, so I guess the speed at which you get to convergence, but also the overall accuracy. And you can see the stability of the training and some of the visualizations that I have of these optimization algorithms. Then we'll look at performance. So I guess a lot of that is how is it being optimized. So we have this compute cluster, and there are a number of ways that you can basically take your gradients across the cluster and average them and combine them, whether it's synchronous or asynchronous. And so we'll look at Spark's model for that. Finally, looking at future work for this package, and then jump into how you'll do deep learning in Spark in general. So there's this basically history of projects that are trying to make deep learning on Spark work, and I want to show you the upsides and downsides of taking particular angles of attack on that. Finally, we'll look at deep learning outside of Spark if we have time and finish up. So first on framing convolutional neural nets. I want to start talking about structural assumptions, automated feature engineering, and learning representations, because from the perspective of a data scientist, you want to know when you should use what tools, and this is extremely important for that. So first on location and variance. Basically, convolution has this really valuable property of basically assuming that anything that is not local is zeroed out. And so what that does in the context of image processing is say you'll have an image, say of an audience, and that image will basically have a number of filters that are dragged across it. And the locality allows you to basically say that basically pixels that are close to one another are going to have interactions with one another. And then at the next step in the hierarchy, you will combine sets of pixels that had interactions with one another locally and start to learn this feature hierarchy. And so you can see in this image that you're only looking at a small subset of the data. And that's actually a really strong prior, that the only interactions that you care about in your data are going to be local interactions. And that's actually extremely efficient because in general with networks, if you have a fully connected network, you're going to be assuming that there's equal weight between the prior on the interactions between your features. So every feature will be interacted with every other feature. And in this context, assuming this particular structure lets us search function space for functions that are going to take advantage of that localized structure. And so in the context of image processing or natural language processing or audio processing, this structural assumption is extremely valuable. The second is learning hierarchy, a hierarchy of abstractions. And so basically at the low level in image processing, you'll have pixels and you'll have curves. And once you move up the hierarchy, you'll basically recombine those pixels and curves into higher level objects, like shapes. And those shapes will recombine into like the shape of a face or the shape of an eye if you're doing facial recognition. If you're on ImageNet, like coloration will also play a part. But basically, this set of levels of abstraction lets you do a number of things. So one is that you will have this high-level representation that can be ported to another context. So you'll basically be able to do transfer at different levels of abstraction in the hierarchy, which means that if you, say, train a neural network on ImageNet, you can take the lower-level representation, which is going to be similar to the lower-level representation in some other data set, and then do very efficient transfer learning because you're taking advantage of that lower-level structure that exists in data sets that you'll see in image processing, but also in audio processing and natural language. This is well explicated in this sort of Zieler-Fergus paper where you can actually get visualizations of the filter maps by basically doing what's called deconvolution. So you'll try to go back to the original image and see what types of object activate your filters. And in this case, the lowest layer, you actually see extremely simple, colorations and these lines or edges, and it basically is a reasonable model for almost every image data set that you'll see. So those feature maps transfer very efficiently to other data sets. Basically, the features that are being learned here are coming directly from the data. And so it's extremely powerful in that whatever it is that you're optimizing for, you will learn a representation that is most likely to make that prediction. So your gradients are basically trying to say, update these filter maps so that I can classify, the body of images that I'm looking at most accurately. This also makes transfer learning feasible. So these lower level image representations can be transferred to another data set and speed up training dramatically. And in general, there's also transfer internally inside the data set. And we can see that with this sort of compositional structure that we learn. So here you're thinking about this hierarchy of abstraction. So there are a lot of ways that you can get a hierarchy. One way to get a hierarchy is, say, recursively. So you'll stop at the top of the hierarchy, and you'll cut the top version into subparts, and you'll cut the subparts into subparts, and you'll end up with this top-down structure. But composition has this bottom-up structure to it. So you'll have a number of low-level pieces, and you'll be recombining those pieces with one another. And in those recombinations, you'll basically have extraordinary expressive power. But in a lot of cases, you'll actually capture important structure in the data. So we already talked about how image structure has this, nice pixels to edges to shapes to parts to objects, like sort of hierarchical structure. But that also occurs in language. So, at the character level, you'll sort of recombine characters to create subparts of words. You'll create those subparts to create full words. Those words can be combined into short phrases, and those phrases will be combined into sentences. And as far as the meaning of the content of the language goes, you can have a word be a concept, or you can have a phrase be a concept, and the sentence will usually be some composition of sets of concepts. But basically, there's a hierarchical structure in terms of the literal way that the English language is laid out, but also in terms of the way that it's laid out conceptually. And those recombinations allow you to basically interact with the data at the level of abstraction that's optimal for making whatever prediction it is that you care about. But it also lets you more efficiently transfer from information that you have from one set of data points to another set of data points, because there's more generality at some levels than others. So basically, as you move up the abstraction hierarchy, you'll get more and more generality. So I guess in the case of images, you're basically finding a compressed version of the image that you can feed to a linear classifier. So there's this phonemes to words structural assumption that you also see in audio processing. Basically, when you're looking at this audio stream, you can imagine thinking about it at the word level and that being the level that you care about. So you're trying to say, figure out what words people are saying inside of the audio stream. But there's basically sets of frequencies that are composed into the word. And so our language has, at a character level, this sort of makes sense that you're going to, for each character, say something that sounds similar. And those are things that you'd like to transfer across different data points. And it's by recombining these small sets of characters that you end up with phonemes, and those phonemes get recombined into different words. And so this compositional structural assumption is actually very useful for a number of categories of data set. And so in those contexts, we've actually been able to improve on the state of the art dramatically using deep learning. And that's extremely important. So what comes out of learning with these different types of structure is a number of amazing applications. So we've basically gotten to a point where doing object recognition in a lot of cases is easier with a network than having a human look at the data. That object recognition and localization and image segmentation has been rolled out in umpteen examples. You saw the drone example earlier today. About autonomous cars and how they've been using all of these tools. They also work really well for image restoration. So one thing you can do is take the most likely pixels that you would have if you increased the grain of the image, or if you basically we're going say from 480 to 720. It's okay, what's the most likely sets of pixels, and can we interpolate? So you can use it for image restoration, for music recommendation. So if you're Pandora, you'll ask, okay, here's this set of audio streams. One thing we can do is attach high-level concepts to each song and say, okay, well, you like hard rock, and so we're going to try to give you more things like that. But you can also, at a lower level, say, here are a number of songs in a genre, and what are the lower-level features that are actually predictors of our genre, and how is our intuition for this song belonging to this genre being constructed? And there's this sense that you can get a much more granular representation of what it is that people like about music by looking at lower levels in the hierarchy and sets of recombinations in that hierarchy. And so you can use ConvNets for music recommendation. It's being done at Spotify and at Pandora. RNNs have also gotten state-of-the-art in a lot of these natural language tasks. And in parts, it's because you can do sequence learning with RNNs. And in general, machine learning models will have this fixed input space, which really limits the type of task that you can point them at. But RNNs have been extremely useful for doing all of the number of language tasks, including speech recognition, QA, machine translation, et cetera, et cetera. Final set of assumptions. So basically, weight sharing is extremely important. So it allows you to basically take a filter map in an image and try to apply it to every single set of features. And it comes out of the homogeneity of, say, an image or an audio stream. So I guess every single set of features that you have is the same. So it's either all pixel values or all frequencies. And that lets you share information across the image or across the audio stream. It's really valuable. But there's also this sort of combinatorial flexibility that you get. So in general, in machine learning, you want to be able to represent the function that is closest to the data generating distribution function. So the data has some structure, and you want that function to represent that structure. And this gives you lots of flexibility in searching for that function in space. Basically, when you do this sort of compositionality, all of the different recombinations of your features are possible outputs for your network. And that combinatorial structure lets you combat the curse of dimensionality. So you can also do automated feature engineering. So basically, the feature hierarchy in general is too complex to engineer. If you try to have your data scientist take a set of images and have them figure out which sets of pixel combinations are going to give you some higher level feature, and then take those higher level features and try to recombine them, the data scientist isn't going to be able to accomplish the task. Basically, the space is extraordinarily high dimensional, and the grain at which the human mind interacts with the data is not appropriate for doing that category of feature engineering. So you can automate this for feature hierarchies, and this works really well for compositional structure. In general, you run into an overfitting problem if you're not doing automated feature engineering over compositional structure. And so there's a sense that DL may be a panacea, but it seems like for contexts where the structure of the algorithm matches the structure of the data, we're doing extraordinarily well. And in other contexts, we have to employ massive amounts of regularization, like dropout or L2 regularization, trying to deal with the fact that our function is extremely expressive and is just going to overfit whatever data it's looking at with a set of assumptions that's different from the structure of the data. So it's not like a general automated feature engineering engine. It's automated feature engineering, but for compositional structure. So this is a great image from Crystal Law. So the representation that gets learned is the one that ideally separates the data. In this case, you have the sort of blue and red classes. Here, they're not linearly separable, but we'll find a representation that will make them linearly separable. And that's by doing nonlinear combinations of the feature input. So I wanted to introduce all of these structural assumptions to MLM. And this is an example of the API that we're basically making accessible, and it's very much like Keras. So it's higher level enough that a data scientist can be efficient about putting their architecture together, but low level enough that you can express whatever type of algorithm that you want. So I guess there was an initial MLM Deep Learning API that wasn't nearly as expressive, and so it was hard to introduce new activation functions and new layer types. But we've opened up the API, and so now you can see that, much like Keras, you'll create a sequential, and you'll add convolution or max pooling layer types to that sequential. You can add activations. Linear ReLU activations are on site here. The dense activation and the softmax layer at the end. And basically, we have an atom optimizer, and we'll fit our model. And the value of an API like this is that basically you can port code that you have in a different context to this MLM API very efficiently. If you're using PySpark, Python side API, it's almost direct. And if you're converting it into Scala, there's this nice one-to-one correspondence between the types of object that you're putting together. So the modularity that you have also basically enables you to do a number of things. So you can do feed-forward networks by, say, adding a dense layer, but you can also replicate logistic regression. So logistic regression is basically this last layer, this softmax layer that we have on top of our network. But we don't actually have to include any intermediate layers. And so you can, with an API like this, just flexibly create logistic regression by having a dense layer and an activation immediately after it, and then optimize it with Atom and apply whatever regularization techniques it is that you want. So this is basically an example of how much you can improve training using momentum. So momentum basically cancels noise in the gradient. So we added this optimizer that will look at your previous sets of gradients and we'll average them together. And so there's noise in every single gradient, but that noise isn't going to be consistently in the exact same direction. And so by averaging together previous gradients, you can cancel the noise and increase your speed in the direction that all of the gradients basically concur that you should be going in. This is another optimizer that we added. It's called RMS Problem. And what it does is it basically automatically tunes the learning rate of every single parameter in your network. And the heuristic it uses for that auto-tuning is taking basically parts of the network that were being trained too quickly in the past and slowing them down, and taking things that were being updated very slowly and speeding them up. And so that makes it possible to use the entire network in terms of the sets of gradient updates that you're getting. And so you got a much more balanced optimization process. In Spark, we have this distributed optimization paradigm. So we basically compute gradients on each worker, and those workers will basically push their gradients back, and on the master, we'll average them. You can see performance numbers here. I'm going to finish up real quick, but basically this access page will give you a link to this SparkDL library. It's also in Spark packages, and so it's accessible here. Also, the slides will be provided. We have some future works. We're working on GPU acceleration, the Python API, and Keras integration. And that's everything. Thanks so much. Yeah. Yeah, sure.
We are going to host all these slides online on our SlideShare account. We'll also create a list of all the resources that the speakers are sharing with you, the papers they're mentioning, the code samples. We've started that so far at mlcomp.com/blog, but we'll be updating that lifetime as we see more resources. So if you have any questions regarding that, feel free to ask me at the break. Please help me welcome Qiaoling Liu from CareerBuilder. Thank you.
Hello, everyone. My name is Qiaoling Liu. I'm from CareerBuilder, and I'm a data scientist. So today I'm going to talk about one challenging task in the online recruitment domain that is called employer name normalization task. So this task links employer names in job postings or resumes to entities in an employer knowledge base. So we have examples. For example, we have you can list some candidates from work from Macy.com or Microsoft, and we need to recognize those companies. And also for the job postings from CareerBuilder or from Microsoft, we need to recognize them too and link together so we know how many jobs are provided by CareerBuilder, how many candidates have worked for Macy's before to do better matching. So this employer name normalization task can be seen as a domain-specific case of entity linking task, while traditional entity linking task links entity mentions in text to entities in often a global knowledge base like Wikipedia. Employer name normalization task links employer names in jobs or resumes to entities in employer knowledge base. And therefore, this task has some common challenges as the entity linking task, but it also has some unique challenges. So some common challenges include handling name variations and handling irrelevant or unlinkable input data. But there are some unique challenges, such as we need to deal with the specific structure from job posting or resumes, and we need to leverage some of the available context there, for example, website or, for example, location. And one more challenging task here, is how to handle the duplicates or noise data in the knowledge base. For example, you may find many different entries for that same company. So we propose 2 levels of normalization to handle those challenges. First, entity-level normalization to handle the first 4 challenges, and then class-level normalization to handle the last one. And entity-level normalization maps a query to an entity in the knowledge base that best matches the query. So for example, the query Walmart Pharmacy, it will match directly to an entity called Walmart Pharmacy. Whereas cluster-level normalization maps a query to a cluster of entities, for example, Walmart and Walmart Pharmacy, they actually both map to the same company, Walmart Store, Inc. And this is the overall architecture of the system. So we rely on 2 kinds of data inputs. One is the knowledge base, and the others are some independent mapping data sources. And we have several important steps like indexing, clustering, and then retrieval, re-ranking, and validation. So we will first talk about the entity-level normalization. One key feature here is we use some external knowledge based on mapping sources to do query expansion. For example, we collect all the Wikipedia mappings using the redirections, such as IBM Corp redirected to International Business Machine Corporation. So we collected all such mappings. And also from the stock website, MSFT means Microsoft Corporation. And we got some other mapping sources as well from some third-party data providers. And so we first use Lucene indexer to index all the available data. The first index is for the KB, the second index for the mappings, and the third index is for the cluster. So the next step after we indexing, now we have an online query, and then we do the retrieval. So we first use Lucene searcher to retrieve top 1,000 entity. After that, so here we use the query expansion, like if the query is MSFT, we will expand to Microsoft Corporation. And so after the query expansion, we will have we hope to have all the correct results included in the top 1,000 entities. And then the second step, we try to do some filtering and to boost the correct result into the top 10 or top 20. And the next step is use learning to rank to re-rank these top 10 or top 20 results so that the best one is ranked at the top. So we use some features like query features, which include whether this query has a location context or whether it has a URL context, which may indicate the difficulty of the query. And then some query entity features, for example, the Lucene score indicating how where the query matches with the entity document string, or whether their location matches where their websites match. And the third types of features are entity features. Some entities are more popular because they are larger company like Walmart, right? So it is highly more likely to be matched as a result. So we use these three types of features, and then we use learning to rank to rank the best ranking based on these features. We use the coordinate ascent method implemented in RankLib library, and this listwise method can help us directly optimize the P at 1, the precision at 1 metric. And the last step is validation. So we want to know whether that top 1 result predicted by the previous step, is it a good result or not a wrong result? So we use a binary classifier to tell us the answer. And the next, after we have the entity result, next we want to avoid some duplicate results. So instead of saying Walmart for this query, Walmart pharmacy for next query, we want to cluster all the different results so that only one Walmart is returned. So we do a clustering level normalization. So we again use the mappings we collected, and we do a graph-based clustering based on these data sources. First step, we created an undirected graph based on the mappings. So we will connect two nodes if they have a mapping in some data source. And the next thing, we want to remove some low-quality edges that only appear in one data source. So we use different independent sources to ensure the quality of the edges. And then we do just do a transitive closure algorithm to find all the connected components and as a cluster. And we also, again, use a learning to rank component to find the best representative entity in each cluster. So here we can learn that Walmart Stores Inc. is the best one to represent that cluster, whereas Target Corporation is the best one to represent that cluster. So we have some experiments based on this system. We chose some real-world data sets from jobs and resumes. And we have different data sets because they can have different characteristics because some data set can have country specified, location specified, or URL specified, whereas others do not. And we use precision and coverage as a metrics. So this shows that the best system, so our system, CompanyDepot, performs the best compared to some of the other third-party service and our previous systems. And for cluster level data sets, we also collected one resume data set and a job data set. And we use we propose some new metrics for this purpose. And so on one hand, we want the results to be correct. On the other hand, we want the results to have less diversity as possible. And that's why we propose success rate to measure the correctness and the diversity reduction ratio to measure how much diversity we reduce, and then use an F-score to measure the overall performance. And the labeling required is the same as how you measure the entity-level normalization, just to label whether a result is correct for a query or not. So we show that based on these metrics, the cluster-level normalization result system performs better than the entity-level normalization system. And we apply the system onto the applications in CareerBuilder called candidate search. So after you search for a candidate, and there are some facets showing the previous employers of these candidates, and we can see the left figure is using the entity-level normalization, and the right part is using the cluster-level normalization. So we can see the correctness of the data remained, but a lot of diversity reduced. And in this talk, I presented our system for the employer name normalization task. And in the future, we have there are a lot of opportunities that machine learning can help. First one is how to automatically learn to merge some clusters, mixed clusters, or merge some duplicate clusters and split mixed clusters. And then we also would like to develop more features to deal with the query segmentation. And as well, the last challenging task is how to improve the quality of the knowledge base. Okay, thank you. So if you have any questions, you can contact me. Oh. Yes.
Does anybody in the audience have any questions for Qiaoling?
I'll be glad to answer your questions, if any.
Can you tell us like some of the things you do with Lucene?
Oh, with Lucene? Yeah. We use Lucene a lot. So in this project, we use Lucene to index our data, like the index, the knowledge-based indexing, and then the mapping indexing and the clustering indexing. And we also use Lucene Searcher to do the basic retrieval step. So that will let us to retrieve the relevant entities, like the top 1,000. After we get the top 1,000 entities, we hope to use some heuristics, domain knowledge to help us locate the best possible correct result, and then we will boost them into the top 10 or top 20, and then we use the learning to rank to help us rank these best candidates and then give the best result at top 1. So I think Lucene is the basic of the system.
Do you guys suggest for your resumes, like, do you have your parsing technology?
Yes, yeah, we do have also resume parsing and job parsing systems that also rely on our machine learning technologies. Yeah, but that's not, yeah, it's out of the scope of this talk because we rely on the parsing result, right? They will pass the resume or jobs and tell us, okay, these are the recognized raw employer names. Please try to link them or understand them. Yes?
So what percentage of these clusters do the job, like, its users care about? Like, are there some that, like, percentage?
Yeah, I think that's a good question. Actually, I think it's application-based. Like, we also have different applications using the system, and they would argue, should we return different level of Walmart, like should we return Walmart pharmacy instead of the whole Walmart stores Inc.? Because some people, some candidates, they may just be interested in the pharmacy jobs, right? So this will be an issue for some applications. They may prefer refined level of entities be recognized. But some other applications, they just need a super entity like Walmart. Anything related to Walmart or subsidiaries, just give us Walmart. So I think this depends on different applications. And actually this system, one benefit is it can build different clusters for different applications. So that can give you this flexibility.
Thank you, Qiaoling.
Thank you.
Please help us welcome Hanjun, a Ph.D. student at Georgia Tech.
Is it working? Okay, thanks. So I'm Hanjun, and currently doing my PhD study in Georgia Tech. I'm going to talk about my research work on learning to represent a graph using deep neural network approach. So graphs are very commonly used data structure, and they have many applications. For example, given a molecule structure, we are interested in predicting its property value, and it can be used for drug discovery. And in the recommendation system, where you have a user item bipartite interaction graph, we are interested in predicting a pair of user and items. And also for knowledge graph, if you want to do some reasoning or question answering with the help of knowledge graph, typically you need to learn the representation of the graph. And finally, there are many NP-complete problems which are on graphs, such as the vertex cover, max cut, traveling salesman problem. This is the outline of today's talk, and before going to my approach, I'd like to give a brief review of the existing approaches. First, about the predicting molecule or RNA sequence property. So given an RNA sequence, if we are interested in predicting its binding affinity, which can be simply treated as a binary classification problem, one approach is to build a dictionary of features where each feature represents a substring of your existing sequences. And you can convert the RNA sequence into a back-of-words feature representation. And it is similar for the graph, but the graph is more challenging since you need to deal with the different size of the graph, and you also have the alignment problem. And one application is to predict its power conversion efficiency, which can be characterized as a regression problem. And similarly, you can build such kind of dictionary where each keyword in the dictionary is a subgraph or the graphlet of your molecular graphs. This approach typically needs to have two stages, where in the first stage you need to build a kernel matrix, where you need to characterize the pairwise similarity between your instances, or you can simply use, like I previously mentioned, backwards features. But typically, this kind of approach are not that scalable for millions of data. And in the second stage, you will build a, say, SVM on top of your feature. But the problem is your constructed feature is not aware of your downstream task, which means those features may not be discriminative enough. And the second example is for the temporal recommendation, where your user item interaction contains the time information. In other words, we are interested in predicting who will do what and when. So typically, commonly used matrix factorization may not be a good choice because it simply ignores the time information. And although you can simply divide your timeline into epochs and do the matrix factorization within each epoch to characterize the changing feature of the user item, but then the problem is how you can divide the timeline. And the final example is on the graph combinatorial optimization. So for example, in the social network, if you are an advertiser and you want to advertise your product such that more and more users will be exposed to the advertisement. So this can be simplified as kind of a minimum vertex cover problem, where you want to pick as few nodes as possible, but at the same time you want to cover the entire graph, entire edges in the graph. And it is known to be an NP-complete problem, but there are some approximation methods for that. For example, you can sequentially pick those unpicked edge and add them to your cover set. But these kind of rules are manually defined, and typically they don't take the graph structure into consideration. Then the question is whether we can learn something better. Okay, so next I'm going to introduce our approach. And instead of doing mathematical way, I like to give it a more intuitive explanation. So take the image as an example. You are already familiar with the convolution on the image, where you apply the filter on each local patch, which means you define such a neighborhood, and you apply the same operator on each neighborhood. And we can make analogies to the graph case, where you do the filter on each one-hop neighborhood. For example, if you have such kind of molecular graph, and we associate the vectorial representation for each node, where each vector can be treated as like channels in the image case. Like each pixel have multiple channels, and here each node in the graph have different dimensions of the representation. And you can gather the information from the neighborhood node to update the embedding of its own node. And then, okay, now it's time to put it together. So given a molecular graph, we associate each node with an embedding vector. And in order to update the embedding of the node 2, we gather the information from the neighborhood embedding and also the neighborhood features. For example, in molecular case, the feature can be the atomic number of those atoms in the neighborhood. And we do this for all the nodes at the same time. And typically, this process can be iterated through multiple steps. For example, if we iterate it through T steps, then you can imagine each node will capture a longer range of information within T hops. And finally, we aggregate them together through some attention mechanism or weighted combination to get the vector representation for graph. And this can be trained end-to-end with the supervision. For example, the energy of that molecule can be a supervision, and the entire framework is trained end-to-end. We did some experiment on the RNA sequences and molecules. For example, this is one type of regression problem, and comparing to the second best baseline, which is the either string kernel or the simple deep neural network or deep convolution network, we gain much better performance regarding the regression loss. And for the molecule case, this is one application used for screening the organic solar panel materials. And the data is taken from the famous Harvard Clean Energy Project, which contains 2.3 million molecules. And yeah, again, we can get a much better regression loss. And also, there's a trade-off between your model size versus your performance. So in this figure, the horizontal axis represents your model size, which equals to the number of parameters. And the vertical axis represents your mean absolute error, and the lower the better. And our approach is here. And if you simply use some graph kernel, you will get something here, which with a very large model. And if you apply some hashing to reduce the model size, you will suffer from the poor performance. So in other words, the embedding methods can get a much compact model and at the same time improve the performance. And also, this kind of approach can get some interpretable results. For example, for the RNA case, we can draw some so-called sequence logo, which captures some position-specific information that you learned from the data. And for the molecule case, we can also use an attention mechanism to highlight those very important fragments in the molecule. For example, we learned that such kind of fragments are very predictive for the higher efficiency value. And we have extended this approach to the network analysis and the recommendation system. Here is an example. Suppose you have a social network where you know some are good guys and some are bad guys, but you only have a partially labeled data, and you want to infer the labels for the rest of the user. The modification is simple. You just modify the loss function to each of the node in the graph instead of a single objective function for the entire graph. And we apply this approach to some document classification in citation network, where we outperform some unsupervised embedding methods like the NoteVec or DeepWork. And there are also some benchmark datasets on the social network and the Wikipedia dataset. We gain a lot regarding the F1 score here. Okay, then come to the recommendation problem. So what we do is to unroll the user item interaction through time. So here we get such kind of dependency graph where the user and the item feature will evolve after each event happens to them. So if you unroll through the time, you'll get such kind of a dependency graph, and you can abstract it as a kind of directed graph and apply the same trick we used before. But the problem here is you only have one gigantic graph, and to make the training easier, we apply some stochastic methods and also use the truncated backpropagation through time, which is also a standard trick in training the recurrent neural network. And here are some experiments. We did some experiment on the TV program recommendation, our restaurant recommendation on Yelp dataset. And regarding the accuracy of the item prediction and also the return time prediction for user, we can much better performance over the baselines. And we found it is especially suitable for those recurring event recommendation. For example, you visit the same restaurant multiple times, or you watch the same TV program multiple times. Okay, finally, I'd like to talk our recent work on the graph combinatorial optimization. I still take the minimal vertex cover as an example. So, there may be some problem with the display, but I want to say there are typically two different types of methods. One is based on the branch and bound. It's a method which can guarantee to find the optimal solution, but typically the time cost is exponential to the size of the problem. And another method is the heuristic or greedy method, where you can have some approximation guarantee, but typically the performance is poor. But I think the most severe problem of these two existing approaches is that they cannot learn from the solved instance to gain experiments for the future tasks. So in real-world data, typically the graphs are sampled from some common distribution. For example, a social network, one can use the Barabasi-Albert model, which is kind of a scale-free network, and the distribution of the degree follows some long tail observation. And also for the road network, typically you have a fixed graph, and the only thing changing is the weight on the graph. For example, if it is a traffic network for the Atlanta, and typically the traffic is very severe in the morning, and it gets even worse in the afternoon. But this kind of changing is on the same graph. So a direct method may be to use supervised learning, but the problem is it's very hard to get the supervision, because solving such kind of combinatorial optimization on a large scale is already hard for the. So we propose to use the reinforcement learning to solve this problem. And the principle is learn by trial and error. So here's a little bit background about reinforcement learning. So suppose you're teaching an agent to play the breaker game, and the reward at each time step is the score you can earn at this time point, and the state simply represents your screen. Your action, you can only move your board to the left or to the right. You have two choices. And there is a concept called action value function, which characterizes your expected future reward. And finally, the policy, which indicates how you will behave at each time point. So suppose if you have a very perfect action value function, then you can simply use a greedy policy, which means at each time point, I only pick the action which can maximize my future total expected reward. Similar on graph case, for example, the vertex cover, our objective is to minimize the number of nodes we picked. So the reward is simply a constant, which is a -1. This means each time you made an action, you will get a constant penalty 1 or reward -1. And the state is simply the currently partially solved solution, which contains the node you already picked and the node you haven't picked yet. And the action value function is on the rest of the node. And we simply use a greedy policy because we assume we have learned such kind of perfect action value function, which means each time we only pick the best node. And yeah, the difficulty is how to parameterize your action value function. And the answer is to use our graph embedding framework. Like here, we take a partially solved graph as input, and the output is the predicted score on each node, which equals to the action value function. And we use some standard framework called deep Q-learning, which fits this kind of equation. I want to elaborate it more because this is more of a standard trick. Okay, so here are some experimental results. First, we sample some scale-free networks, and on this bar plot, our performance is barely visible because we can get almost perfect approximation ratio. The ratio equal to 1 means it's perfect, and typically the ratio is larger than or equal to 1. The lower, the better. And also, this approach can not only generalize to the graphs from the same distribution, but it can also generalize to larger instances. For example, we train our model on a small graph which contains only 50 to 100 nodes, and we can generalize to up to thousands of nodes. And of course, the larger the instance, the harder the problem, but we can still keep the ratio low, below 1.007, which is almost perfect. And also there are some trade-offs between the time and your solution. Typically for the brute force search or heuristic search, the more time you give it, and the better performance you will have. And for example, for Cplex, which is a commonly used toolkit, at the beginning they can get a very poor result, but in a short time. And later on, with more iterations, they can get a better performance. And here are some performance plots for the approximation methods, which are fast but with poor performance. And this is our approach. We within 0.1 second, we can get the best performance, almost comparable to the Cplex with more than 100 seconds. And we can also apply it to real-world data. For example, this is data taken from the Stanford website. It's a mem tracker graph. And we sample some subgraphs, learn from them, and generalize to the entire network. And our solution is only, we will only pay one more node for comparing to the best optimal solution. And here is an example. I'm not sure how to play this video, but so here I just want to say we actually learned a heuristic which is not discovered before. Comparing to the heuristic, like you always pick the node with largest degree, we can pick the nodes while maintaining the connectivity of the graph structure. This is a heuristic that I haven't discovered before. Yeah, and also we can generalize to other combinatorial optimization problems. For example, the max cut, where you want to divide the nodes into two separate components and maximize the edges between the two components, or the classical traveling salesman problem, and also more general, the set cover. Yeah, finally, I'd like to take this chance to say thanks to my collaborators and my advisors. Okay, thanks for listening.
Ladies and gentlemen, do you guys have any questions?
Yes, please.
So you made that example where you have the example with the Emacs, and then how you parallelize your example of the graph, right? So you take your one, your neighborhood for your shipment.
Yeah.
So does your output depend on the graph structure at all?
Yeah, it depends on the graph structure. Like for different nodes, they have different number of neighborhoods, and you need to make the operator more general. Instead of in image, you always have a fixed size of a patch, but on graphs you have different number of neighborhoods. So one approach is simply pull them together, like pooling using max pooling or average pooling, and another approach is to use some recurrent neural network to get some operators that can generalize to different lengths of the neighborhood. Yeah.
All right, ladies and gentlemen, I think we're all set. Can we get a round of applause for Hanjin? And if I'm not mistaken, I believe we're taking a break for lunch. So ladies and gentlemen, I'll invite you guys outside where we have lunch served, sandwiches and things of that nature. So we'll see you back inside in a few.
Sure.
My name's Owen King.
Nice to meet you.
Here's my card.
Okay.
I was interested. I am just learning about machine learning. This is all very new to me, but some of the things that you said stood out to me and could be interesting. In the mining space, which is where I operate, is your graphing techniques going to be more powerful because they are a three-dimensional type way of analyzing data, as opposed to crunching data numbers to find an answer? Is it possible that your way of looking at data would be more powerful at predicting three-dimensional shapes?
Three-dimensional shapes. But if that's is there a graph or simply a three-dimensional image? Or?
So what I have terabytes of data.
Okay.